Okay, now we move to exercise 9 of topic 11. In this case, we have two infinite planes of charge that have negligible width, therefore we can assume that they are extremely thin, and are parallel to the YZ plane. So we can plot them in this YX plane. So this will be our two parallel infinite planes of charge. Then one is placed with respect to x equals 0 at x equals minus 2, so it's on this side and has a linear surface charge density of minus 3.5 microcoulombs per meter square. Okay, so it's units of surface charge density. While the other is at positive plus 2 and has a larger surface charge density and positive of 6 microcoulombs per meter square. Now, we had to determine the electric field at this side of the first surface, so at the left side of both infinite planes, in between the two, and also to the right. Okay, so I'm going to do this a bit smaller so I have more room to actually do the numbers. But the important, we are going to make a first draw here just to have an idea of the signs of the different components of the electric field of the different vectors. That's going to be important. The other thing to keep in mind is because we have infinite planes, the electric field generated by each of them is going to be constant, right? Not going to depend on the distance to the surface. It's just going to have a given value. What is the value? So E will be equal to the surface charge density divided by 2 times the permittivity of vacuum. Okay, so that equation is that we are going to use to compute the contribution of each of the planes to the electric field at the 3 different positions. Now, the important part here is that we have to evaluate first the electric field in absolute value that each of the 2 planes produce, and then the signs of the vectors of the electric fields produced by each of the planes, depending on where you are evaluating the electric field. So if we first, for example, compute these numbers, the electric field produced by this surface, that will be equal to the sigma, which is, in the case of 1, is minus 3.5 10 to the minus 6 coulombs divided by meter square, divided by 2 times 8.85 to the minus 12. Yep. Same. Second, yeah, coulomb square divided by Newton meter square. That's a 12. Okay, minus 12. Okay, so 1 second. It's pretty more clear. Okay. Now, if we compute this will be equal to 1.98 10 to the 5 newtons divided by. Okay, that's the electric field produced by 1. Does it make sense in terms of units? Yes, this goes with this one, meter square, and we end up with newtons divided by coulomb, which is units of the electric field, of course. Now for the second surface, then of course we have 6 10 to the minus 6 coulombs divided by meter square, divided by 2 times 8.85 10 to the minus 12 coulomb square divided by Newton meter square, which in this case is 3.39 10 to the 5 Newton divided by coulomb. Okay, so those are the absolute values of the electric field produced by each of the 2 surfaces. E1, which will be the electric field produced by first infinite plane, and E2 will be this one. Of course, because they are homogeneous, but sigma 1 has a smaller in absolute value, smaller charge surface density, also the electric field produced is smaller. It's slightly above half, because this number is slightly above half the positive charge of the second plane. Now, for the different sections, A, B, and C, we are asked to compute this at different sides of the two surfaces. For x to the left of -2, we have to plot here. That's going to make it larger. So that will be, we have to compute it. This is sigma 1, this is sigma 2. We have to compute it here, right, on this side. Now, if we do it in that side, that means that, remember, this is sigma 1 is a negative charge, so that means that the electric field produced by sigma 1 is going to go this direction, so that will be E1 on this side and E1 on this side. Okay? Same thing here, of course. E1, because it's homogeneous, and E1. Now, what happens with E2? By the way, E1 here also will go this direction, of course. It will be always pointing to the negative surface charge density. What happens with E2? Well, E2, which is here, is positive, so it's pointing that direction. So that means that E2 will be going that direction. The same thing with E2 here. Same thing here with E2. And of course, E2 now, because this is positively charged, on this side, E2 will go in that direction. Again, it's homogeneous, so it's going to be the same value here, the same value here, and so on. Okay? Now, that already is telling us what's happening for section A, B, and C of the problem. So what is the electric field on this side, on that side, on this side? So when we compute it to the left of the first plane, of sigma 1 plane, what we get is that the two vectors are in different directions, and actually E1 is positive and E2 is negative. So that means that if we do it for section A, what we will obtain is that we'll have this vector E1, which is our electric field, will be equal to the first component, which will be pointing to positive values. So that will mean that this 1.98 10 to the 5 y vector I Newton divided by Coulomb, right? That will be the first vector, is positive sign, right? It's pointing to the right, and the E2 is negative, so that will be minus, make the marks here just to make clear, so that will be 3.39 10 to the 5 I Newton divided by Coulomb. So that will be the first electric field, so it will be the add of the two. So it will, because they are parallel, we just can basically add together the two vectors. That will be equal to minus 1.41 10 to the 5 10 to the 5 I, vector I, Newton divided by Coulomb. Okay? So that's the value of the electric field in the case of A. Now, for the value for the position in between the first and the second plane, which could be in this position here, right? What we have is E1 is negative, E2 is negative. So in that case, if we remove, for example, this part here, right? For P, what we'll have will be the 2 will be negative, so that means that we'll have minus 1.98 minus 3.39 times 10 to the 5 I newtons divided by Coulomb. So that will be for B, which is minus 5.37 newtons divided by Coulomb, which is the number that we have here. Okay. Now, of course, for the part C, what we have is that the two vectors now have, again, opposite directions. The E2 is larger than E1, and therefore these two terms here that we have for when we compute it for this part, now they have different signs. So will be minus 1.98 plus 3.39 10 to the 5 I newtons per coulomb. So that gives us an electric field which is the same as this one but positive. So it's plus 141 10 to the 5 I newtons per coulomb. Of course, you have to, at the end of the exercise, it's always good to check that things make sense or not. Remember that we said that this sigma 1 has less surface charge density and is negative than this one. So that means that when this vector is positive and the other one is negative, because E2 in absolute value is going to be larger because the surface charge density of the second plane is larger, it implies that, of course, on this side, the net electric field has to be positive, okay? Because it's the electric field of sigma 2 is always dominating over the electric field of sigma 1 when the two have different signs. So, of course, in this side dominates the sign and the direction of the sigma 2 electric field, so that means that it's positive, 141, and on this side, which is the one that we compute here, we have E1 going to the positive, but E2, which is the dominant one, it goes in the negative direction. So that means that the electric field will be pointing, the net electric field will be negative, which is actually minus 1.41 10 to the 5 I newtons per coulomb. Okay, so that was exercise 9.